Welcome back to The Deep Dive, the show where we take that fire hose of information, all the articles, the research, the technical guides, and we really just distill it down into what you actually need to know.
Today we are diving into what I think is the future of so many applications. Production LLM engineering. I mean, the models have already changed so much.
Oh, absolutely.
But the consensus is that the next 5 years will see them, embedded so much more deeply into our systems.
Okay.
They're moving from being a novelty to just a reliable utility.
And reliable utility is the perfect phrase for this, because we're not just talking about, calling an API. We're talking about building really robust, scalable products,
Yeah.
like the LLM twin system
Yeah.
from our source material. So this deep dive is pulling directly from the blueprint in the LLM Engineer's Handbook to get to the core patterns in the toolchain you need.
And we really have to start with the engineering pain point this whole thing is trying to solve. When engineers build ML systems, they often end up with these complex, monolithic batch systems.
And they just don't scale. Everything is too tightly coupled.
Exactly. And in the LLM world, that tight coupling is a total nightmare for real-time systems. If you need external context like RG documents or user history.
Right. You fall into that anti-pattern of making the client carry the entire state. You're suddenly passing these massive contexts with every single call. It's slow, it's expensive, it's just not scalable.
It's not. The client shouldn't have to know how to compute or access all the features the model needs. And, while there are these hyper-optimized custom solutions out there, I mean, we saw mentions of some really complex Google Cloud architectures. They get so intricate that only a handful of people can even maintain them. And that just defeats the whole purpose of engineering for stability.
So our mission then is to unpack the structure that solves both of those problems, the complexity and the scaling. Okay, let's unpack this. So the big solution from the source material is this FTI architecture, feature, training, and inference pipelines. Tell us why separating things like this is so transformative.
It really acts as an architectural mind map. Instead of seeing this one giant impenetrable block of code, FTI gives you 3 distinct logical layers.
Okay.
And the brilliant part is that each pipeline feature, training, inference, is made of components that can run on totally different processes, different hardware.
Or even be managed by different teams using different tech.
Exactly. It enforces that modularity right from the very beginning.
So if your data engineering team wants to use one system for creating features, and the deployment team wants a separate, highly optimized service for inference, FTI actually supports that.
Absolutely. And you get this massive secondary benefit. It inherently solves the training serving skew problem.
Which is this perennial headache in ML where your model is great in training.
And then it just falls apart in production because the live data is just a little bit different.
Right. But FTI avoids this because the features are created using the exact same code in both the feature pipeline for training and the inference pipeline for live predictions.
That's it. Consistency is just baked into the architecture. And the way these pipelines talk to each other is key. They only communicate through data storage.
The feature store and the model registry.
Precisely. The feature pipeline creates features, puts them in the feature store. The training pipeline pulls from that store, trains the model, and puts the weights in the model registry.
And then inference just looks up the latest model and pulls the context it needs from the feature store. So the feature store is more than just a database. It's the consistency engine.
That's a crucial distinction. It's a managed database for ML features. It ensures consistency, and critically, it often gives you time travel capability. So if you need to roll back a bad feature transformation, you can debug against the exact data state the model saw.
Okay, so now that we have the architecture straight, we need to talk about the software that manages it all, the MLO stack. This is where we shift from architecture to the specific LLM engineering toolchain.
And at the very top, gluing it all together, you need an orchestrator. The source highlights ZenML for this. It lets you take standard Python functions and just decorate them with @pipeline or @step.
And they just slot right into the FTI flow. That sounds like it removes a ton of boilerplate code.
It does. It manages all the artifacts and metadata. But once that model is trained, it needs a home.
Which is where Hugging Face comes in as the model registry. It's the standard, really. The central place for models, version history, all that metadata that's so crucial for CI/CD.
Yeah, your deployment system knows exactly where to find the right versioned weights and config.
And of course, running those training jobs, you have to track everything. Comet ML is mentioned as the experiment tracker. What are engineers looking at beyond just, training loss?
Oh, they're looking for bottlenecks. They track evaluation loss, sure, but also things like the gradient norm to see if convergence is smooth. More importantly, they're watching system metrics.
Like GPU memory usage, CPU load.
Exactly. If your GPU is sitting idle half the time, you've got a very expensive problem.
Right. And for the, let's call it the plumbing, poetry is there to handle Python dependencies. That poetry.log file is so underrated, but it's key for reproducibility.
Absolutely essential. And for the data itself, we need two different kinds of storage. First, MongoDB, the NoSQL workhorse, for all that raw, unstructured text scraped from the web.
And second, the VectorDB, which is just so central to these systems. The recommendation here is Qdrant. Why Qdrant?
Well, the source says it offers a really strong production-grade trade-off between requests per second, latency, and index time. It's just built for high-throughput Gen AI.
Now, there's one more tool in this stack that's often overlooked in traditional MLOps, but is like absolutely critical for LLMs.
Prompt monitoring.
Prompt monitoring. This is where OPIC comes in.
Yes, OPIC or something like it is crucial because
Okay.
the prompt is the new code. The model's behavior changes constantly based on the inputs. OPIC lets you track the quality, the cost, and the latency of your prompts and outputs in real time. If a RA prompt suddenly starts giving weird results or costs spike, you see it immediately.
That visibility is everything. And speaking of RAG, let's pivot to Retrieval-Augmented Generation. Since it leans so heavily on that vector stack, here's where it gets really interesting.
RAG is the tech that basically solves the two biggest challenges you face when you deploy a static LLM.
Which are hallucinations.
Right.
And the model just having old, outdated information.
Precisely. By giving it factual context, you dramatically reduce the chance of it just making stuff up. And for the old information problem, RAG is a shortcut. Instead of spending millions on retraining, you give the model access to new knowledge instantly through retrieval.
And this whole thing pivots on embeddings. We hear that term all the time, but just remind us, in practical terms, what are they?
They're dense numerical representations. Vectors. They can have like 64 to over 2,000 dimensions, and they just capture the semantic meaning of something. If two documents are conceptually similar, their vectors will be close to each other in that high-dimensional space.
Which is a space so complex you need visualization tools like UMAP just to project it down to 2D or 3D so a human can even see the patterns.
It helps you intuitively grasp what the model is seeing. And that brings us to the VectorDB. A traditional database looks for an exact match. You search for LLM, it finds LLM.
But a VectorDB looks for semantic similarity. It's doing a closest neighbor search using something like cosine similarity.
Yes, and as we said with Qdrant, a production VectorDB is so much more than an index. It's enterprise-ready, it has CR'd operations, security, but the key feature is metadata filtering combined with vector search.
And that metadata filtering is the secret sauce for advanced RAG.
It is.
If I ask about the impact of FTI on MLOps, I don't just want similar documents. I might only want ones written by, say, authors in the engineering department.
Exactly. Filtering on that structured metadata before the similarity search is what makes RAG so powerful and accurate.
And to get even more accurate, the sources talk about advanced pre-retrieval techniques. First one is query expansion.
This is a really clever tactic. Instead of just using the user's query, you use a small, fast LLM to generate variations of it. So how to structure LLM projects might also become best architectural patterns for LLMs.
So you generate more vectors, increasing the chance of a good match.
Okay.
And the second technique, self-querying, is even more sophisticated.
With self-querying, the LLM becomes a parser. It actually extracts structured metadata from the user's query, like a date range or a product name, and passes those as filters to the VectorDB along with the query. It just prunes the search space down so much.
Those retrieval techniques then feed into how we customize the LLM itself, which is fine-tuning. Let's talk about the two main types.
First up is supervised fine-tuning, SFT. This is really about teaching the model new skills and, manners. You use curated instruction answer pairs to teach it a specific chat format, like the alpaca template.
And the second is preference alignment, with methods like DPO, direct preference optimization. This is less about facts and more about subjective preference.
Right. You use these preference datasets, chosen answers versus rejected answers, to align the model with a certain tone or style or safety needs. So if you want the LLM twin to mimic the author's unique voice, DPO is how you do that.
And for SFT, you can't just use any data. The source mentions 3 dimensions for high-quality data: accuracy, so it has to be factually correct; diversity, covering lots of use cases; and complexity, so it requires multi-step reasoning.
That quality is so important because while full fine-tuning gives great results, it's computationally destructive. It takes huge amounts of VRAM, and it can lead to catastrophic forgetting. where the model forgets general skills.
So engineering reality pushes us toward parameter-efficient techniques. This is where LoRa, low-rank adaptation, is the hero.
LoRa is non-destructive, and it just dramatically cuts down on memory and time. You inject these small trainable matrices into the big frozen model.
Hmm.
For an 8 billion parameter model, you might only be training 0.5% of the parameters.
That's incredible. You get almost all the performance with a tiny fraction of the compute.
And then QLoRa, quantization-aware LoRa, pushes that even further. It uses things like 4-bit normal float quantization.
And the efficiency gains are
What?
stunning. The source showed up to a 75% reduction in peak GPU memory. A 7B model that needed maybe 14 gigs of VRAM could be fine-tuned with just over 9. That democratizes access to this powerful technique.
So once the model is all tuned up, we have to deploy it. Which brings us to the monolithic versus microservices choice.
For production LLMs, it really has to be microservices. A monolith is simpler to start, yes, but it ties your expensive GPU resources to your cheap CPU resources running your REST API.
Which is just massively inefficient. Your GPU is sitting idle while it waits for some business logic to run on the CPU.
The microservices approach solves this by decoupling. The LLM microservice runs on its own specialized, expensive GPU VM, and the business logic runs on cheaper CPU machines. You scale them independently. You optimize your cloud bill.
And whether you choose online real-time, asynchronous, or offline batch, the constant challenge is just speed, always speed. And that means inference optimization. The first must-have is the KV cache. See, when an LLM generates text token by token, it has to recalculate the keys and values of all the previous tokens.
That's so much redundant computation.
It is. The KV cache just stores those previous results. It acts like a short-term memory buffer, so it doesn't have to do that work over and over.
And then there's continuous batching, often using page attention. Traditional batching wastes so much GPU memory because it reserves space based on the longest sequence in a batch.
But prompts and generations have wildly different lengths. Continuous batching dynamically manages and shares that GPU memory across all the requests. It means the GPU is almost always fully utilized, which just skyrockets your throughput.
And finally, we're back to quantization, but for deployment. Just reducing the precision of the model weights to save memory.
Yep, from, say, 32-bit floats to 8-bit integers. It's essential for fitting big models onto the hardware you have. The key is knowing which format to use. GGUF and llama.cpp are great for CPU inference, maybe with some GPU offloading.
Like on a standard laptop.
Right. Versus something like GPTQ or EXL2, which are designed for pure, dedicated cloud GPU throughput, the fastest possible results for real-time serving.
But deploying the model is just the middle of the story. The final layer is robust LLM and monitoring. And the key difference from DevOps is that change can be triggered not just by code, but by data or model changes too.
And you need visibility into all three.
And before anything even runs, you need guardrails. Input guardrails to protect against things like prompt injection.
And output guardrails to check for sensitive data leaks or, harmful outputs. The trade-off you have to accept, though, is that these safety layers add a bit of latency.
Monitoring goes so far beyond just infrastructure health. Because LLM outputs are streamed, you have to track these very specific metrics that define the user experience.
There are three critical ones. Time to first token, TTFT, which is how quickly the user sees something. Time between tokens, TBT. And the overall tokens per second, PPS. If your TTFT is high, the user thinks the whole thing is broken.
And in the complex RX system we've been designing, you need full end-to-end visibility. You log full traces, which you can see in tools like Langfuse, to debug the whole chain.
By tracking latency and token count at every single step, retrieval, embedding, generation, the guardrails, you can instantly see the bottleneck. If retrieval is taking 800 milliseconds, you know exactly why the user is waiting.
So what does this all mean? We've gone through the whole blueprint. We started with the FTI pipeline as the architectural mind map, layered on the MLlogs toolchain with ZenML and OPIC, used advanced RAG, got efficient with QLAR, and optimized deployment with continuous batching.
It's an integrated blueprint that ensures engineers can deploy models reliably and, maybe most importantly, cost-effectively. And that modularity from the microservices design is just paramount.
Right. The source material really drove that home. You could upgrade just the LLM microservice, maybe jumping from an 8 billion to a 30 billion parameter model, and leave the business logic API completely untouched. That's real future-proofing.
It is. But making a leap that big from a model that fits on one GPU to a giant 30 billion model that introduces a whole new set of scaling ceilings.
Which makes us wonder, how does the need for advanced model parallelism techniques, like pipeline or tensor parallelism, further influence the design of the microservices needed to support that massive jump to a foundational LLM in a production environment.
That's the real frontier of LLM engineering. It's where infrastructure, data science, and architecture all meet the absolute limits of modern computing. Something for you to mull over as you design your next large-scale system.